All right, guys, let me try to catch up to you. On this first one, what's n going to be? 14. Of course, p and q, we're assuming it's fair coin. And that kind of leads to some math shortcuts. I'm not going to even apply it, but I'll let you guys figure it out for yourself if you want to. I want exactly 9 heads, so how would I set up that equation?
14 choose 9.
Good. 14 choose 9.
Times 0.5.
So I want 9 successes. So how many failures?
5.
5. So that overall I have 14 things. So when you multiply all that out, what do you guys get?
0.1222.
1222? Yeah. So about a 12% chance to get exactly 9 heads. I like this. What about the probability of at least 1 head? This might have freaked a few of you guys out a little bit. But at least 1 head would so suck, because I have to do this formula. I'd have to do it for 1, 2, 3, 4, 5, 6. I love it. There you go. I love it. You guys are like, why are you doing that shit, Jeff? Perfect response. I'm crying. This is what I say. That's 1 minus the probability of none, or no heads. Let's say I. So what's the probability of 0 heads? Be 14. Choose 0. 0.5 to the 0. 0.5 to the 14. And what do you guys get for that? You end up getting like 6 point something times 10 to the negative 5?
Yeah.
So you get 1, 2, 3, 4, and then a 6. So if you said it was approximately 0, that's actually okay, since we normally do like 4 decimal places. But just to show you, approximately 0 doesn't mean it's never going to happen. This does not mean it's never going to happen. It just means it's really unlikely for it to happen. So if it did happen, that would be decent evidence that something is wrong with that coin. Evidence, not proof. So how do I get what I actually want? 1 minus this would be 0.99994. Yes?
This probably is the same. Instead of writing it out, 0.5 to the 9 times 0.5.
You say 0.5 to the 14 for everything. Yes, that's the shortcut I was talking about. Yeah. All right, is everybody cool with that first couple problems? I mean, those first couple problems at this point should be semi-easy to set up. They have to. Formula kind of sets itself up. If you know how to do binomial PDF, that's really nice. You don't have to know how to do it, but if you do, you can check your work. This is not work. If you think pushing buttons in a calculator is work, then something is wrong with your perception. Your last teacher thought it was, and something's wrong with their perception. I don't want to hear about it. Now, this line here we're used to. We know these formulas. These formulas kick so much ass. They're the best mean and standard deviation formulas we've seen yet. So NP would be, N is 14, P is 0.5, so you get 7. So of course you'd say, if I just asked you on the first day of this class, if I flip a coin 14 times, how many heads would you expect to get? You would say 7, of course, right? Now does that mean you're always going to get 7? No, but it should be close to 7. If the coin is a fair coin, it should be relatively close to 7. The next line down from this, once we figure out the standard deviation, is that idea of, well, what does close mean? How far away from 7 is like where things get a little bit weird. So what's the standard deviation going to be? It'll be square root of 14 times 0.5 times 0.5.
1.87.
1.87. 1. Okay. Remember, standard deviation always at least 3 places. Right? Whatever, Jan. Yes. So now, I'm going to talk in a little bit about exactly why this is true. But if I go 2 steps out, 2 standard deviations out in both directions, and every step is the average distance away to the data points, 2 steps out should catch a lot of the data points, if you think about it. So we'll talk a little bit more about that in a minute, but right now, just this gives me an idea of what usual is. Anything outside of this range is unusual. So would 8 heads be unusual? Even before I did the calculation, no, that's fine, it's expected, it's close to 7. Would 1 head be unusual? Yeah, that would be strange. To get 13 tails and 1 head would be a little bit strange. So let's see what the range really is. So the mean, if I do 7 minus twice 1.871, what do I get?
3.26.
3 point,
265.
what do I get? 258, okay, I got you. Sure. So that's the lowest usual value. And it's an average, that's why it's not, you can't get 3.258 heads, Jeff. I don't care, it's an average. It can be any number it wants to. And then it would be up to, let's see, 3 point, so like 10.742. Ha ha ha. So 11 heads technically would be unusual because it's outside the expected range, the usual range. Would 11 heads be really unusual? No. But it would still be evidence of something a little bit wonky, possibly. Right? Is 11 heads impossible? Of course not. It's just really unlikely. All right, let me stop there for a second. So this whole idea of, we've talked about this off and on for a little while. I have an average and a standard deviation, but how does that relate to where unusual is? Like what would be unusually tall or unusually short? You can do this exact work. What's the mean height? What's the standard deviation? Go up and down 2 steps. That's the usual range. Anything outside of there is a person where you would do a double take because you don't see that everybody, whoa, you're tall. Right? If you see somebody 5'7" walking down, I'm not going to go, whoa, you're 5'7". Because that would be a usual height to expect. Right? Unless you're 3. All right. Now this is now here is my attempt to connect the binomial problem, the probability, with what we were talking about here with areas. So here is we made a table like this just a minute ago. We went 0 through 5, and I made you guys all the rows. Well, most of the rows did this. All the rows try to do their own problem. So we made it. So this is really just 14, 2, 0, blah blah blah. The one we just did. See what the 0 plus then means? What's 0 plus mean? It means really close to 0. So 0.00006. I would say that's really close to 0. So 0 plus means not 0, but really close to 0. You guys see that? Okay. So that's the table. If you do the formula for every single one of those possible number of successes, and this is just the histogram made off of that table. So help me out. What's this one go from to? 4.5 to 5.5. I like it, right? That's the whole the limits versus the boundaries, so that they'll connect and there won't be any gaps in between. All right, let me let that sink in. So what's the area of this rectangle here? It would be, how wide is it? 1. That's the height, and that is the probability of that. So if I wanted another probability of at most 6 heads, at most 6, what's at most 6 mean? 0, 1, 2, 3, 4, 5, 6. I would just take the area from 0 to 6, add up all those areas, and that would be the probability. Or you can see it as just take 0 through 6, add up those probabilities, you get it. Okay, I like it. Let me stop there. So you can take any probability situation. If you can graph it, you can then relate the probabilities to the areas associated to the questions asked. Now these, again, this is beautiful because these are freaking rectangles. That kicks ass. Area is easy, right? And then, of course, you've got... So whatever the hell that all adds up to be. Anybody do that?
0.395.
395? Okay. If you add up 0, 1, 2, 3, 4, 5, 6, you get 0.395. That sounds familiar. Oh, it should be 0.395. It does sound. I've been using this worksheet for like 14 years or something crazy. You're old, Jeff. Shut up. Yeah, so this is what I just said. Rectangles, easy. And then you got this uniform probability distribution, which is actually even freaking easier. Because every little rectangle it's made of is the same height. Holy shit. So remind me, if it went from 7 to 23, how tall would that be? What would the height be if it went from 7 to 23? What would the height be? Yeah, it'd be 1/16. I like it. 1 over b minus a. 1 over the highest minus the lowest. So the overall, the area comes out to be 1. I like it. Now, so those are all easy. And hopefully I've got you guys to understand that area is very much closely related to the idea of probability. They are very closely related. They're the same in these situations. When I make the area 1 of a total thing and I want a piece of it, the area is the answer. Just like the dartboard. So what sucks about this, if I wanted to know, so this is a normal distribution. If I wanted to know the probability it went from here to here, you can just read it off there, but why is it 34%? How the shit would I get that? What's the area? Is this a trapezoid? No, because this side is curving. Now, you do not have to know calculus for this class, because we're going to have a computer that knew calculus is going to give us all the freaking answers we need. Here, like next time we'll do that. Oh, that's a phrase you got to be careful with, because then people start to pack up. It's not time yet. But basically, one big thing calculus does is it gives us a way to calculate the area under any shape. It's crazy. That's one thing calculus does. If you've never taken calculus, you have no idea what the hell it's about. That's one thing it does is it helps us figure out the area under any shape. Thank God for that, because, I mean, if the probability of something is related to the area, I have to have a way to figure out the area. If I don't, then I'm just as screwed as I was before I knew it was related to area, right? So let me talk a little bit about, let me fill in some gaps about the normal distribution, and then I'll do a little preview of what's coming, and then we'll probably head out a little bit. Well, we'll see. It's a little early by the time I get done talking. All right. So that back side of this handout we'll be doing next time. So make sure you bring that. Is this guy still there? So there was something back in chapter 2 that talked about normal distributions and how the probabilities kind of fell out in those. Kind of were distributed. Guys, hey. If you need to talk, you can head out. So if I have a normal distribution, it's kind of nice. It's very well known. It's a shape. It's got to follow a few rules. The middle's got to be the highest point, but it's actually a little bit more than that. It's a little bit more. To be a normal distribution, you must. Let me see if you guys can handle this. Whatever the mean is, let me right now just put the mu. What's the z-score for the mean? Always. Yeah, because what's the z-score formula would be x minus the mean divided by standard deviation. Remember that guy? So the z-score for the mean is always going to be mu minus mu. It's going to be freaking 0. How far away from the mean is the mean? Freaking 0. So I'm going to represent this with a 1. And what does that mean? It's the mean plus 1 standard deviation. I'm not going to do the minus 1 is the mean, minus 1 standard deviation, of course, and so forth. So then I've got 2, 3, negative 2, negative. Sort of almost symmetric there. So here's a few facts about this. This is really nice. If it's a normal distribution, it cannot escape these facts. There will be 68%. It's actually like 68.26. This is like a rounded number, but there will be that much percentage of the data within one step. Okay. And then if I go out one more step, there'll be 95% of the data there. And then if I go out one more step, there'll be 99.7%. It's kind of freaky. But it makes sense because most of it's got to be in the middle. Then it goes down sharply. So there should be, most of the data should be within 3 steps away. Because every single step is the average distance to the data point. So 3 steps away should capture most of the data. Now, do you see why on the handout it said max and min usual would be within 2 steps? Because if I take 2 steps up and 2 steps down, I catch 95% if it's a normal distribution. And to be honest, I'm not going to get too deep into this, but there's actually something called Chebyshev's theorem. I always call him Chubby Dude. No idea the poor guy was chubby or not. But within 2 steps of any distribution, it doesn't matter what it looks like, within 2 steps you would catch at least 75% of the data, which is still a really good chunk. So that's why we decided at this level, right now, later in the semester we're going to change this up a little bit, but right now, 2 standard deviations away is where unusual starts. So if you had a height that was a z-score of 2.5, then you have an unusual height, right? You are more than 2 standard deviations away from the expected height. Okay, I like it. And that really kind of gets into something we talked about on the first day is, well, what would unusual be? How far away would it get to be unusual? Would it get to be unexpected? Okay, so that I just wanted to throw at you a little bit. They talk about this in section 2.7. This little picture here. Okay. Now, this is called the empirical rule. And it only works if it's perfectly normally distributed. So very often, we need to know a distribution. If it's normal, that's awesome. We know a lot of the answers. We know all the answers. This by itself is nowhere near good enough, though, to be honest. What if you wanted to know what's the probability it's between 0 and 1.17? Can the empirical rule help you out? No. You'd only understand 0, 1, 2, 3. But let me ask you this question. Don't say anything out loud. Just hold on to it a second. Can anybody figure out what's the probability for a normal distribution that the z-score is bigger than 2? So what would that look like? Can you shade it on the picture? Where would z bigger than 2 be? Can you shade that in? It'd be right here. Forever, right? Can you figure out what that probability is based on just these things that we know? You should be able to. So for example, well, what percentage is from -2 to 2? 95%. So what percentage is outside of that? So what percentage is on that side? 2.5%. There you go. So there are some probabilities you could figure out that are more than just these 3. You can actually cut them in half and stuff. That's where they got the 34 and the 34. Remember what's true about a normal distribution? It is perfectly symmetric. So the middle will always cut things in half. Is that cool? This is some groundwork for chapter 6, which is coming really fast. So probably z greater than 2 would be 2.5%. What's the probability that z is between -2 and 1? Take a minute. Try to figure that between -2 and 1. There's several kind of different ways to do this.
Is it 81%?
Maybe. And this is really almost separate from statistics. It's just really, can you work with the numbers in the areas to get the area that I want? That's not a statistical problem, to be honest. It just happens to be true that area is related to probability. That's how it relates to this. So what area do I want? I want, let's see if the red one works. Ooh, I can get it really high. So I want this area here, right? -2 up to 1. So somebody want to tell me what's one way that you did this problem? Anybody?
I did 95 minus 68.
So if you do 95 minus 68, that gives you what? That gives you these two.
Divide by 2.
Divided by 2 will give you this one. I like it. So 95 minus 68 is,
13.
well, 95 minus 68 is 27. Cut in half is 13 and a half. So this would be 13.5.
Plus 68.
So then you just add it to 68, and that would give you this. Do you guys see how to do this? You can cut the areas in half around the mean. You can subtract them. You can do all these different things. So this is not even a statistics problem. This is just a, can you work with the numbers problem? Really? What's the difference? Anybody get the answer to do it different? The answer would be 81.5. Anybody do it a different way? Yeah, I don't. We all did it the same way, Jeff. That's the way I did it. All right. Then nobody did it a different way? Okay. Does it make, even if you weren't sure how to do that, do you see how to look at that? Now, that doesn't help me get any questions that are in between 0, 1. There's no way to do that. Why can't I estimate it? Because it's not a line. I can't do like an approximation because it's curvy. So it's changing how much it's decreasing or increasing. Holy shit, this is where calculus comes in. Thank God we're not going to use calculus. I'm not going to suddenly teach you calculus in a day. Right? We're going to just use a table of values showing most of the z-scores out to 2 decimal places. So we'll be able to do something like, what's probably that z is between 0.49 and 1.82. We just have to look up the areas on the chart. I like it. I know a lot of my colleagues are like, well, just use the buttons on the calculator, John. There's something to be gained by using this chart a lot. You start to realize how areas are distributed in the normal distribution. And this is something that's important to kind of have a feel for. So I have a reason, a method to my madness. Okay, what time we got? I think. Is that what I want to say? Yes. I think that's pretty good. Wow. So next time we're going to do, don't forget to bring back that sheet. We're going to look at the back of this, and I'm going to have that table of values that you spoke about. We'll figure out how the hell to read them to answer these questions.